Our lesson today is lesson 8.4, part 1. We're going to talk today about the equations of a sinusoidal function. So remember that great big crazy sounding name just means a sine or a cosine function. A function that has a regular, periodic, repeating period. Okay? So today we're going to identify the characteristics of the equations of those functions. Now just a couple things we need to remember, and that's the first one is, remember whenever you're dealing with the trig functions, sine, cosine, tangent functions, you need to be in radian mode. And so remember, just a quick review from last day, the mode button is beside your second button. If you click on that, you'll see the third line down. Your calculator will function in either radian mode or degree mode. Right now, degree mode is the one in dark, so that means my calculator is calculating in degrees. I need it in radians to do questions that have to do with sine, cosine, and tangent, so I just toggle down to it, and once it's flashing radian, I just hit enter, and then it makes radian modes highlighted. Okay, then I can clear my calculator, and I know my calculator is now functioning in radian mode instead of degree mode. Also, this asks us to set our window settings for this. So these will be your X settings, these will be your Y settings. Okay. So go into your window, set your settings as -2 pi. Remember, you have a pi button, second function of your up arrow. And when you hit the down button, it will change that to -6.28, because if we know that pi is 3.14, then -2 times pi is going to be -6.28, right? Makes sense. Okay, then your X max is going to be 2 pi. And when you go down again, it will switch that to 6.28. Your scale is going to be pi divided by 2. And then again, change your Y's to -2. And then +2 and a scale of 1. Okay? All right. So then we can go back to okay. Once we have our windows set, then we can have a look at what the actual equation of a sine function would be. Okay? And I'd like you to write that right beside this word investigation at the top of your page. Okay, the function of a sine, or the equation of a sine function is y equals a times sine, and then in brackets, bx plus c brackets plus d. Okay, so remember last day when we were talking about just a regular plain old basic sine function, y equals sine x. Okay, I guess that's here. Okay, your basic sine function is y equals sine x. And we learned last day that there's some certain characteristics that are always the case for y equals sine x. It always will have y-intercept at +1, a y-intercept at -1. Okay, it also has a period length of 2 pi. So if this is measuring in pi's, 2 pi would be here. 1 pi would be here. Okay, so half of pi is pi over 2. And so if this is 1 pi over 2, this is 2 pi over 2's, which in lowest form is pi. This is 3 pi over 2's. This is really 4 pi over 2's, which in lowest form is just 2 pi. So then our regular sine function y equals sine of x would look like this. It would go down through this point. So we'd go up to a height of 1, then down through this point to a height of -1, and then like that. Okay, so it has one period that is 2 pi long. That represents one complete rotation of 360 degrees if it was on the unit circle, right? It would go all the way around from 0 or 2 pi all the way around to 2 pi. Okay, the midpoint is pi, just like it is here. This is half of pi. This is 3 pi over 2, right? So this is 1 pi over 2, 2 pi over 2, which in lowest forms, the 2's cancel out and you're left with pi. 3 pi over 2, this is 4 pi's over 2, which in lowest forms is 2 pi. Remember all of this? Just as a quick review. Okay, so this that you see on the graph here, this graph of a y equals sine x function has a period of 2 pi, and that represents one complete rotation if it was on the unit circle or on a Cartesian plane. Okay, but when we see it on a graph, it looks like this. On your x-axis, it goes up as high as +1 as its maximum, and down for a minimum of -1. Okay, so that's the regular characteristics of a basic sine function. However, like I said last day, sometimes we mess with that function a little bit, and we add a value in front that's multiplied by the sine function. Okay, that's the a value, and today we're going to investigate that a value. Sometimes we even add a b value, a c value, and a d value, and when we do that, it just changes those characteristics. It might change the period, it might change the maximum and minimum values, it might change the horizontal placement of that graph on the x and y axis. So we're going to learn today how changing each of those factors will affect this basic graph of a sine function. Okay, so I'm just going to erase all of my scribbles here so we'll be able to do this investigation together. We've got our windows set, so we can start to investigate the a value. So that means if we have a function and we take our regular plain old y equals sine function, and instead we're putting something in front that we're multiplying y equals sine x by, like 2 or 0.5, what happens then? Okay, so let's go into our y. Whoop, my calculator just turned off, so I just need to turn it back on. Go into your y1, and I'd like you to put y equals sine x as your y1. Okay, and don't forget to close the bracket, and then just ask it to graph, and you should get that graph that I just drew a minute ago. Okay, so this is a lesson today where you're going to need 3 different colors in order to differentiate between the 3 different graphs that we're going to draw. So if you need to pause the video and find 3 colors, then restart the video once you have them. Okay, so this first one, y equals sine x, I'm going to draw that one in red, so I'm going to put a circle there to show that the red one is this graph. Okay, and again, I'm going to just mark it. It would go up to 1, but it will come back down through there. Then it will go down to -1, and it, whoop, and it will come back up. Okay. Okay. So I'm going to just put some basic information here. I notice that my a, in this case, what is the value of a in this basic sine function? A is this number that I'm multiplying in front of, like y equals something sine x. Well, in this case, my a is really 1, right? So a stands for amplitude. When we talk about the amplitude of those waves or the curvature, the amplitude is this distance here, remember, from the midline up to the maximum point, or from the midline down to the minimum point. Remember that from last day? And I'm going to erase this here so that I can see. Okay. Okay, so my amplitude is 1, the distance from my midline to the maximum point, or the midline to the minimum point is 1. Okay, and I also can determine on this basic sine graph where my midline is. The midline is that point right in the middle, so that the distance above to your maximum is the same as the distance below to your minimum. And so in this case, my midline is at y equals 0. Okay, That y, the x-axis is my midline in this case. Now I wonder what happens and how this graph changes if I put in 2 times sine x. Okay, so again on your calculator, go into your y equals, leave your original in there so that we can compare it, and just go down, and we're going to change the line on this so that it'll be a nice thick line, and it will look a little different then. We'll be able to see a difference between our two. So if you toggle over to where the line is flashing and you hit enter, you'll get a thick line. Then go over and enter 2 sine x and ask it to graph that. Then you'll see the second graph, and what do you notice is different about this graph? Yes. Okay, so if we're going to graph this, let's use a different color. So I'm going to use blue for this graph. And I notice that this graph is going up to a maximum of +2. Okay, so I have a maximum point here and a minimum point of -2. Okay, it's still going through this point, and it's still going through this point. It's just going higher on these curves than the original. Okay, so what's changed here is that my amplitude has become 2 instead of just 1. The distance from my midline to the maximum point, or my midline to the minimum point, is 2, isn't it? Okay, and what about my midline? Has my midline changed? No, my midline is still y equals 0, right? This is still my midline. Still the spot where the distance to the maximum is the same as the distance to the minimum. Okay, well, let's put this third one into our calculator now. Go back into y equals, go down to y3, and again we're going to change to a different type of a line, and you do that just by hitting enter. There's my thick line, hit enter again, and I've got, and if you just keep hitting enters, I'm going to do it with dots maybe. Let's see if that will work. And I'm going to now go over and put in 0.5 times sine of x. And when I hit enter, our graph, okay, kind of what I expected to happen. This time my amplitude, the height of each wave, is only going up to 0.5 as my maximum and -0.5 as my minimum. So it's going to here and to here. It's still going through this middle point, so I can draw it like this and like this. Okay, so this time my amplitude is 0.5. What about my midline? Right, my midline is still y equals 0. Nothing has changed there. Okay, what has in fact changed? By changing this a value in my original equation, so by changing this number that I'm multiplying in front of sine, I change my amplitude, right? The distance from my midline to the maximum and the distance from the midline to your minimum. That's what has changed, okay? Okay. Then let's do the same. This time we have 3 more that we're going to graph, and so we're going to clear this time our y's. So in here, you're going to clear out y1, y2, and y3, and then start from scratch. And this time enter all 3 of those equations. Enter the first one as your y1, the second one as your y2, and the third one as your y3. Okay? Maybe pause the video and then restart it once you're ready for that. Okay, so when you've got them entered in and you hit graph, let's see what happens to our graph this time. There's our original y equals sine of x. This bold one is what, but with a negative sign in front, I guess. The bold one is -2 times sine of x. And this little one that is drawing right now is -0.5 sine of x. What do you notice has happened to our graph? Right. In the original graph, our period was starting from 0 and going up, above the x-axis before coming down below the x-axis. In this case, our whole graph has been taken and flipped around the x-axis, hasn't it? So what was above is now below, and what was below is now above. Okay, so let's draw what that looks like. So again, you're going to need your three colors. We'll graph this first negative sign of x. Was the exact same as the sign of x. It had a maximum point of +1 and a minimum point of -1, but it went down first instead of up. So we're going to put a point at -1 here and a point at +1 there. It still goes through this, so it's going like this time. And then again, back down through -1 here, +1 here, so something like this. Okay. Then our -2x did the same thing, but it went twice as deep with the amplitude to -2. Everywhere where this one was a -1 or a +1, now it's a -2 or a +2. Okay, so we can draw it again, going like this. Okay, and then the last one, our green line, is -0.5. So again, our amplitude this time was only going to positive or -0.5. So again, this A value, the number that we're multiplying sine by, did affect the amplitude, but when it was a negative number that we're multiplying sine by, it actually flipped the whole graph about that midline. Here's our midline, and it just took what was above and it just flipped it into the bottom, and what was below, it flipped up to the top. Okay, so let's see if we can just summarize here. What has changed? Well, the whole graph has been flipped. The actual mathematical term for that would be reflected about the x-axis. That means around the x-axis. Okay, so these points right here would remain stationary, and the whole thing would just flip. Okay. Okay, so the A value of the graph is equivalent to the, what does the A value give you? This number that was in front here, it gave us the amplitude, right? Okay, it's the amplitude of your graph. The A, if the A is negative, then the graph is reflected about the midline. All right, so let's flip the page and let's see what happens if we mess with the B value. So again, let's just write what our original equation is. Y equals A sine, then bracket, bx plus c, bracket, plus d. So what we're talking about this time is what happens if we change the c by multiplying something by c, okay? So when we look at our graph, we've got two graphs that we're going to investigate this time. The regular, straightforward, basic y equals sine x function. We're going to do that one color. And the other time, when we're multiplying that x by 2, we're going to see what happens, because that's the b value. The b value is the number we're multiplying in front of the x in the equation. Okay, so again, let's go back into our calculator. Clear out your existing y value, y1, y2, and y3. And we're going to go in and we're going to put in these two equations. Y equals sine of x. And then again, change your line to the thick bold line. Is probably the easiest one to see. And this time we're going to do sine of 2x. And close your bracket, ask it to graph. Okay? Okay, that first one is our regular straightforward sine graph. The second one is what happens when we multiply x by some number. What do you notice has happened? Okay, well, first of all, let's draw these. Okay, our regular straightforward y equals sine of x. Okay, we know that it's going to have, it goes up to +1, it goes down to -1, passes through this point. So it goes like this and like this. I'm just going to move this over so I can do this on this side. Okay. And now, when I have put in a value in front of my x, so it's sine of 2x, this is what happens all of a sudden. What do you notice has changed here? Right. Before, my period with a regular sine function, the period is 2 pi, right? The period was this whole distance from here to there before it started repeating again, right? Now this time, that distance has shrunk in half because here all of a sudden is that function to there. And then all of a sudden it's repeating again to there. And then, so it's fitting 2 of those into the space that before one of those fit. So what has changed? Well, the period has changed this time. Okay, so let's go up here. The regular sine function had a period of 2 pi. When we multiplied our x by 2, what happened to our period? If this whole distance here, the red line, the whole distance from here to there, stopping there, if this is one period, and that's 2 pi, then now I have one period that is going from here to here and stopping there. That's half of 2 pi, which is pi, right? This is period that's half the size. It takes half the distance to do one full period of this function, okay? So what has changed? The period. So actually this b value doesn't tell you the period because in this case, the b value is 2, but our period is not 2. Okay, so what the b value tells you is how many complete rotations there would be in 2 pi, or how many complete cycles there would be in 2 pi. So in this distance here, from here to here, that's 2 pi, right? And so this is 1 whole rotation, 2 whole rotations in 2 pi, right? Okay. Okay, so let's just make a note to ourselves here. The b value tells you how many complete rotations in 2 pi there are. Or, you know, another way you could say that is how many, instead of complete rotations, how many periods in 2 pi there are. Okay? Okay, so for each equation, we're going to calculate 2 pi over b. And you'll see why in a minute, okay? So for our first function, it was sine x. If we're going to calculate 2 pi over b, okay, b tells you how many complete periods there were in 2 pi. So in this sine function, that's our red one here, so looking at the red one, how many complete rotations were there in that distance of 2 pi? This whole distance here. Right, there was only one. So our b is 1. Okay, and what is 2 pi over 1? 2 pi. Okay, so, and 2 pi was our period. Okay, so this is the equation here that helps you figure out the period. 2 pi over b will give you the period. Okay, so I'm just going to put that that equals the period of the function. Okay, let's check it out for our other function. Okay, our other function was sine 2x. Okay, so we're going to use this formula again to find out the period. So that formula is 2 pi over b. Okay, what is our b this time? B, remember, tells you how many complete periods there are in this 2 pi space, right? So how many complete rotations or how many periods were there? Well, we had 1 to there, 2 to there. So there were 2. So our b is 2. 2 pi over 2 is pi. Pi was the period, right? Yes, okay. So you can see that this formula here, 2 pi over b, is a formula that will help you calculate the period of a function, okay? We're going to summarize that in a minute, but maybe just make a note to yourself that in the margin here, that this is the formula for calculating the period of a function. And just use the abbreviation for function, okay? So this here, this formula, 2 pi over b, will help you calculate the period of a function. B is not the period, but it tells you how many complete rotations there are in a period, or how many complete rotations or periods there are in 2 pi, I mean. Okay, well let's see what happens then if that number that we're multiplying x by, that b value, what happens if that b value is a decimal less than 1? Okay, so again, go back into your calculator. I suppose you can leave your y1 because we need to do sine of x, and just change your y2 to, instead of sine 2x, change it to sine 0.5x. And close your bracket. And let's see what happens when we graph those two. There's our original, as we would expect. And there's our, oh. That's interesting. Okay, well, let's draw what we got. So again, we're going to use red as our original function. We're going to draw our original function knowing that it has a maximum of 1, a minimum of -1, maximum of 1, minimum of -1, okay? And then I'm going to use blue for the second function. And the second function, that's very interesting. It goes like this. And then it goes, like that. Okay. So what has changed here? The period has still changed, you're right. Okay, so first of all, what was the period of my red y equals sine x function? The period is 2 pi, right? What's the period of my blue function when I've multiplied the x by 0.5? Right. this is one complete period right to there. So the distance from here to there this is 2 pi plus another 2 pi. That's actually 4 pi distance that it took to do one complete period or one complete rotation. Okay? Okay. So for each equation, we're going to calculate, what does this formula give us again? The period, right. So for our y equals sine x function, okay, we have 2 pi over b, and b is how many complete periods there are in the distance of 2 pi? Well, in this case, there is one complete, right? This distance, that's one complete rotation, and that distance is 2 pi. So there's one complete rotation in 2 pi. So the period is 2 pi of a regular sine function. We knew that already. Okay? Let's figure out the period then and see if we were right when we said it was 4 pi, but we're going to use the formula to see if we were right. So sine of 0.5x is 2 pi over b. Well, our b is how many complete rotations or how many complete periods are there in a space of 2 pi? Well, in a space of 2 pi, that's like from there to there. Well, there's only half of a rotation, isn't there? Okay, so what's 2 pi divided in half? 4 pi. Okay, so this equation will give you the periods of these two functions. Okay, so when we go back to our original equation, y equals a times sine of b times x plus c plus d. We now know that if we change something here in front of the word, in front of the sign, it changes the amplitude, the height of my waves, the distance above the midline or the distance from the midline to the minimum point. But now I know if I change this number and put something in front of the x, multiply the x by something, then actually I'm changing it affects the period, right? Now that b doesn't tell me what the period is, but it tells me that the period is being changed, right? Okay, so let's see if we can answer this. So if the absolute value of b, in other words, the positive value of whatever we're multiplying that x by, is greater than 1, so that was our first ones here, then like this one where we did 2x. Okay, it changed, how did it change the period? The period went from 2 pi to 1 pi, right? So it changed the period in half, didn't it, really? What happened was it took this regular period and it really condensed it or compressed it, right? And all of a sudden we're getting 2 whole periods in the same distance that it took us before to do 1 whole period. Okay, so it is actually being compressed, horizontally compressed. And then the second investigation that we did here, when we changed the number that we were multiplying x by, was between 0 and 1, so it was a decimal between 0 and 1, then what happened to our period? The period that normally took 2 pi to complete now takes 4 pi to complete. Okay? So it actually stretches it, or we call that, it expands it, is the proper mathematical term. Okay, so we say that it's horizontally expanded. And then if that b was negative, then it would again be reflected over the x-axis, actually. So just like before, when that number was negative, it did flip it over the x-axis. It would do the same in this case. Okay, it would still be flipped over the x-axis, but it would be compressed or expanded depending on what number you're multiplying your x by. Okay? Okay, so up here at the top, let's just say here where we put that the b isn't the period, the b is related to the period. Okay, so it tells you how many complete rotations there are in 2 pi. So it doesn't give you the period. Like if that number's a 2 in front of the x, that doesn't mean your period is 2. It means there's 2 complete rotations in 2 pi. Right? Okay. Now I know this is a lot. We are going to continue looking at what happens when we change the c and what happens when we change the d. Okay, so just bear with me. We're going to investigate the c value this time. So again, let's just go back to our original equation. Y equals a sine bracket bx plus c plus d. Okay, so now we're saying, what happens if this value, if there's something being added to your x, or in some cases subtracted from the x, how will that affect the original graph? Okay, well again, we're going to graph 2 graphs, so you can set them up in your y as your y1 and y2. I'm going to leave sine x as my y1. I'm just going to change my y2 to sine of x plus pi over 2. Okay, and when I ask it to graph, we're going to see what happens. We get our original sine equation, and then, oh, well, that's a beautiful design. What happened there? Okay, well, let's draw our original equation. Our original basic sine function looks like this, up to 1, down to -1, one whole complete period in 2 pi, then again the same thing on the other side, okay? But look at what happened when I graphed x plus something, and in this case the something is pi over 2. Well, first of all, before I'm going to try and draw this, I need to kind of figure out what these markers are. Because, okay, if this whole distance from here to here, like one whole period of this function is 2 pi, okay, then I know this is 2 pi, this dot here, okay? And I know then that this dot here would be half of that, so that would be pi, okay? And then, okay, if this distance then from 0 to pi, halfway between that would be half of pi, so pi over 2. And so if this is 1 pi over 2, this is 2 pi's over 2, which, as you can see, your 2's would cancel out. That's pi, right? So then you'd have, what's this point then? 3 pi over 2. Yeah, exactly. And this one technically is 4 pi over 2, because you've got 1 pi over 2, 2 pi's over 2, 3 pi's over 2, 4 pi's over 2. And again, this cancels and becomes 2 pi, right? So that's where this comes from. Okay, so let's do the same then on this side. Then if this would be negative pi over 2, this one would be negative pi, this one would be negative 3 pi over 2, and this would be negative 2 pi, right? Everybody with me on that? Okay. Okay, so now I'm going to mark then in blue. Well, you know what? I think I'm going to switch to green just because I wrote all those numbers in blue. I don't want this to be too confusing. So look carefully at our graph. What happened here on this graph? Let's pick a point on this original red graph. Okay, so I'm going to choose like this point here and look at it, and then look at what happened to it. It has shifted it to the left. How far? Pi over 2, right? So what's happened is this point has now become this point. Okay, so everything has shifted pi over 2 to the left. Okay, so let's see if we can draw that. Okay, so it would look like this. I'm going to just put on here what's happened is it shifted it left by a distance of pi over 2, right? Every point on there has shifted over left pi over 2. Okay, so what has changed here then? We can say the graph was shifted pi over 2. Oops, not that. The graph. Shifted the graph pi over 2 units left. Interesting that it is a shift left when I'm adding pi over 2 to x. We're going to talk about that in a minute, okay? So what's my new starting point, okay? If this was my starting point before at the origin, where's my new starting point now? Right, my new starting point is at negative pi over 2, isn't it? Okay, so now I have here one whole cycle that was originally over here, okay? Okay, let's do the same thing then with, let's see what happens if we add a negative number instead of adding a positive number like we did before. So go back into your y2 and just change it, and you can actually insert. So I'm going to use the second function of the insert and see if I can get that negative sign. Nope, I got it on the wrong side. I must have to be right there when I hit insert. Negative. No. Okay, well, I'll do it old school then. Plus bracket negative pi. Whoop, how come I have a space? Negative pi over 2. Okay, is that what I wanted? Sine of x plus bracket negative pi divided by 2. Okay. And again, ask it to graph. There's my original sine function. And there's my new sine function. Okay, so in red, I'm going to mark my original sine function, which is, I should be getting pretty good at drawing these now. And what's happened now that I have added a negative pi over 2, it's actually moved my complete graph pi over 2 to the right. So where my 0 was before, it's now over here. So now it's going to be, oops, I didn't draw that very well. Okay, so again, what has changed? Well, the graph has shifted pi over 2 to the right. And what's the new starting point for the function now? Well, my original starting point was here. Now it's shifted to here, right? It's shifted over to pi over 2. Okay, so we're going to summarize. At the bottom of our page, you don't have this, or I don't on the smartboard, but I do want you to remember this, okay? So if you don't have a summary box at the bottom of your page. Let's just write this at the bottom. So when we have a function, a sine function, where we are adding something to our c value, okay, and it will be in brackets then with the x so that you know that it's part of the x. It's some way that x has been replaced by x plus some value, okay? And I'm going to give you some examples. Y equals sine x plus pi over 3. Or you might have something where you're subtracting something from x, like x minus 3. Okay? What this is going to do is shift, this one will be shifted pi over 3 units left. Even though it says plus, it's the opposite of that, okay? And this one, x minus 3, that's going to shift 3 units right, okay? So it is the opposite of what it looks like. And if you really think about that, it kind of makes sense, because if you were solving and this was like the 0 of your function, that's going to give you your x-intercept, isn't it? And if you were solving this, x minus 3 equals 0, x is negative 3. Oh, sorry, x is positive 3, I mean, right? Because you'd add 3 to the left side, add 3 to the right side, you'd have x is positive 3. So your x is actually moving positive in a positive direction to the right, 3 units, okay? Same thing here, if you were solving this to get what your x-intercept was, you'd say x plus pi over 3 equals 0, and then x, you'd subtract pi over 3 from both sides. So x is negative pi over 3. That's why it goes left. Okay? So just that it is kind of backwards to how it looks when it is affecting your x value, when it is shifting your whole graph horizontally left or right. You just have to remember it's the opposite to what this sign looks like. So if it's plus, we think it's going right, but it's not. It's going left, okay? And if it's negative, if it's minus, it looks like it should be going left, but it's not. It's the opposite. It's going right, okay? So up here at the top, we're going to write that investigating the c value, changing the c value, this is actually called a horizontal shift. Okay, so when you add something to your x or subtract something from the x, it's a shift left or a shift right. And it is always the opposite of whatever this sign looks like it should be. It's the opposite to that. Okay? Okay, now the last one is actually quite easy. The last one is investigating the d value. And you know, I think maybe we'll leave this one for next day, just because I don't want to overwhelm you with too much, and I know that this is a lot of new stuff. So I think that's as far as we'll go to start. But there is an assignment that I would like you to work on, just so you have a little bit of practice with changing the a, b, and c value on some functions and how that affects their graph. And then we'll do the d and summarize tomorrow.